All right. Thank you all for joining me for part 2. In this talk, we'll be going over immersed curves again, this time applying them to one of the open problems we talked about in part 1, which is the cabling conjecture. So to start this off, maybe motivate it by the example it's known. So if you suppose that our surgery along a knot is reducible, meaning it contains an essential two-sphere, the first example that comes to mind here is the PQ cable of some knot K prime. If we have this for our knot K, then PQ surgery along K gives out a lens space together with the connected sum of P over Q surgery along K prime. And it's a conjecture due to Gonzalez-Acuna in short that this is the only example. So the conjecture goes, if our surgery along K is reducible, then K is a cable knot and R is given by this cabling annulus. The cabling conjecture is known to be true for torus knots, satellite knots, and alternating knots. Here, you think of torus knots as cables of the unknot. All right, so it then kind of suffices to just look at hyperbolic knots. But here, if we know that if K is non-cabled, excuse me, sorry, we do know that for a reducible surgery, R, the reducing slope, is integral, and that our surgery spits off a lens space sum end. So these two facts together tell you that in absolute value, R is greater than 1, thanks to Gordon and Luke. And if K is then non-cabled, then it satisfies a genus bound, given by twice the genus of K minus 1. And I alluded to in part 1 that one approach to studying the cabling conjecture was noticed by Halm, Liebman, and Zufelt, and that was their approach was to use the mapping cone formula for Floer homology to study this like a Heegaard Floer periodicity that they observed. So that's sort of what this proposition is going to discuss. So the breakdown is you suppose that Y is given as the connected sum of some Y1 and Y2. Y1 is an L space. Well, we'll be applying it. Y1 is a lens space on the nose. And Y2 has a finite rank of H over 2. And then in this case, they have this periodicity result, which they show for HF plus, but will then also hold for HF hat. That as the spin C structures vary as multiples of the rank of H over 2 of Y2, then you end up getting isomorphic Floer homology as relatively graded F adjoin U modules. For us, it'll be relatively graded F vector spaces. This comes from an observed Kunath formula for the Heegaard Floer chain complex CF hat of the connected sums. And for our purposes, when looking at surgery, we'll be relating the spin C structures that shift by K. Right, and this was sort of an integral step to their proof that if they start with a hyperbolic L space knot, then it admits at most a one reducing slope. And the slope that it does admit is the bound due to Montignon and Sayari. So this is going to be, the critical tool for looking at the cabling conjecture for thin knots as well. Okay, so briefly mentioned in part 1, but I'll do it here again. To define a thin knot, we need to appeal to the knot Floer homology of a knot. So Ojvan-Szabo and independently Rasmussen, they associate to a null homologous knot. For us, we'll just look at any knot in the three sphere. They associate a bigraded vector space over our field of two elements. The two gradings are the Alexander grading and the Maslov grading. And we say that a knot is Heegaard Floer thin if every generator of knot Floer homology is supported in a single delta grading, which is the Alexander minus the Maslov grading. Alternating knots are known to be thin due to Ojvan-Szabo. Ends up the case that the Maslov grading, wherever the knot Floer homology is non-trivial, you have that the Maslov grading is given by the Alexander grading plus the signature over 2. Okay, so the thing that really enables us to even use immersed curves as a strategy to investigate this problem is that the full knot Floer complex of a thin knot is relatively simple. So here's two examples for the figure 8, which we did look at in part 1. If you remember, the curve invariant HF hat of the figure 8 complement had a pretty simple form where it had a, true to its name, a figure 8, and then a fully horizontal essential curve, and then some grading arrow coming up to meet it. And one of the takeaways here is that this box in the full knot Floer complex is maybe connected with a different color than blue, is related to the figure 8 that you see there and the height that that figure 8 sets at. More interesting things can happen though. You can have a non-horizontal essential component, such as the case for this example full knot Floer complex of some knot that looks like, one part looks like T25, and then the other part looks like 2 boxes. So we have this staircase part, and then the 2 boxes. And this simple form makes it so forming the curve invariant is fairly simple and also easy to work with. So just to capture that, the full knot Floer complex in this case for a thin knot has only staircases or boxes, and they're all length 1 edges, so they're condensed. And then this means that the curve invariant for such a thin knot has either a T2N, so like a 2N torus knot like essential curve that will wrap and snake around the base points, depending on tau of that knot, or and additionally, sorry, has simple figure 8s. So figure 8s where they wrap adjacent base points. And this isn't something that was really mentioned in part 1, but there is a outside of the case when the directed graph for your type D structure of your knot complement is valence 2, then there is a general LOT algorithm to construct the type D structure from the full knot Floer complex. And then Hanselman, Rasmussen, and Watson, in the case that you end up having a vertically and horizontally simplified basis for your full knot Floer complex, they give a sort of like a shortcut version to obtain the desired immersed curve invariant. For our cases, this is true for thin knots, so they're very easy to conjure up. And so here are the curve invariants, just like shown before for the figure 8 complement. This is what looks like on the right when you have that T25 like curve. The T25 part is just this remaining piece, and some facts about T25, you have that for this knot at least, tau of k is 2, the genus of k is also 2, and that's sort of why this curve goes up above this second base point and then wraps down and snakes around. Okay. And then it also has two boxes occupied at heights 1 and -1. So here the figure 8 down at the bottom sits between the minus first and minus second base point. Just for clarification, this is sort of what is meant by heights. You can see that this line, if you don't skip from 0 to -1, this figure 8 exists at height -1 and this figure 8 at height 1. Something to mention is that this can always be the case for a curve invariant. So this is a theorem due to Hanselman, Richardson, and Watson that the curve invariant for a manifold torus boundary is unchanged by 180-degree rotation, or more specifically, this is the action of hyperelliptic involution on the boundary torus with mark point removed. And this is as unlabeled curves. So one thing that you get from this is that you have the same number of figure 8s located at a positive height as you do as that negative height. Okay, so we sort of have all the information from this example, except the weights of these grading arrows are sort of unknown. And we do need to use that if we hope to appeal to anything involving the Maslov grading. So then depending on the height of a figure 8 in the curve invariant and tau of the knot, the weight of a grading arrow, you can sort of show by using the technique in the HRW papers of recovering the knot Floer complex by intersecting with this lift through the marked base points, and then on the left of a base point you'd put a Z base point, and on the right you'd put a W, and then you would just do traditional knot Floer homology that way. If you run through an argument like that, we find that either the weight of this grading arrow is minus tau minus n over 2, or minus tau minus n minus 1 over 2, depending on the parity of tau and n. Seemingly, this breaks this problem up into looking at two cases at every step. But what ends up happening is that in this case, when the weight is minus tau minus n over 2, the way that you have to traverse this grading arrow has you pick up a positive or a non-zero rotation part of the grading difference for the bygone between these two generators here. And when the grading arrow is minus tau minus n minus 1, it resolves itself almost to have this this bend for the non-smooth part of this bygone. And so then when you tally up the smooth rotation components, there's no rotation at all. And so it ends up being that in either case, this quantity of the grading difference is minus 1 minus tau minus n, no matter the parity of tau and n. That's one of the key observations that prevents you from devolving into having multiple cases everywhere. Okay, so I kind of want to just go through, as I said in part 1, the result that I feel confident presenting right now is the one for thin knots. So that thin, for slice knots, that thin slice knots satisfy the Cabling conjecture. A lot of the same techniques are used in the argumentation for the full general thin knots, but this is, I guess, just a taste. So we can assume K is non-cabled, thin and slice, and then do the Montignon-Sayari bound earlier, that if we have a reducing slope, it satisfies this genus bound. If mirroring if needed, mainly for convenience. We just suppose that the surgery slope is positive. Mentioned earlier that if a knot is sliced, since this is a concordance invariant, tau is, then we know that tau is 0. And in the HRW algorithm to go from the full knot Floer complex to the immersed curve invariant, this tells you that the essential component here, gamma 0 bar, is just purely horizontal. And then because the knot is then thin, the rest of the curve invariant is just simple figure eights between adjacent base points. Okay, and the pairing theorem that we mentioned earlier allows us to associate the Floer homology of surgery in a given spin C structure in correspondence with which lift of a slope R curve, the immersed curve for a solid torus, which lift of that solid torus curve crosses the curve invariant. All right, so maybe at this point it's just best just to see an example. I think there's a lot of setup. So let's look at a genus 1 knot, and we have any possible number of figure eights in the middle, so not just one, as the case for a figure eight complement. And one thing that you can notice right away is that this is the line of slope R through height 0, and then these other two are the lines of slope R through height 1 and -1. And if there are any figure eights at all, then there will be a non-trivial amount of Floer homology all condensed in a single spin C structure. And the periodicity proposition earlier, due to Hom, Lidman, and Zufelt, says that if we're going to have a reducible manifold, there has to be some periodicity. And so this leads us to conclude that there can't be any figure eights at all, which would contradict having a genus 1 knot in the first place. So it's sort of easy to see why this example ends up failing pretty quickly. More generally, knot Floer homology does detect the genus of a knot. And so this is really the fact that enables this argument to get off the ground, is that you're required to have a simple figure eight at height g-1 in order for knot Floer homology to be able to detect that the knot is genus G. And intersections between lifts of the solid torus curve and this highest figure eight end up giving you the largest Maslov grading that you could have in that spin C structure. And that largest term, the grading difference between that and some base generator, that grading difference ends up exceeding the possible grading difference in any other spin C structure. And that's sort of how the argumentation will go from here on out. So let's set n prime to be the spin C structure that we know that the lift of the solid torus curve that's filling through will cross through this figure eight at this maximal height. We'll call one of the generators there y n prime, and we'll call the spin C structure that we're focusing on n prime. And our goal is to show that only two spin C structures could have this maximally graded element to support such a wide difference in gradings. We'll have our base generator, everything that we're computing relative to, be the generator with the essential curve, the horizontal one. And we'll define MREL of y to be its Maslov grading relative to this base generator. And then MRN, this multi-set, to be the set of all of these relative gradings in a given spin C structure. Way easier to see in an example, so we'll just go right to it. Suppose genus 5, the surgery slope is 3. In this case, we know that we have a figure eight at height 4. And since the surgery slope is prime, we know that the y2 summand needs to actually be an integer homology sphere. So our periodicity lemma proposition tells you that every spin C structure has relatively graded isomorphic Floer homology. So we should expect to see all these MRN sets to have the same elements. And we go through with the grading formula that we have from part 1, and we see that this just doesn't line up. The highest possible grading that could even occur in MR0 ends up being 2, and the grading that we know exists for y4, its relative grading ends up being 4. And it could be that you could have a figure 8 situated at this height 0, and just like for the figure 8 not complement, this will give you a -1 grading relative to A0. But even then, the width of MR0 would be capped at 3, and we already have that the width of MR1 is greater than or equal to 4. So this does it for this example. This is sort of characteristic of the small slopes, R equals 2, R equals 3. And then when you want to handle larger slopes, we define omega n prime to sort of be, this is the number of columns that the lift of the solid torus curve has to traverse between column 0 and the one where it intersects that final figure 8. It should have been an R, sorry. It'll be a special case when this number is 0, when the lift intersects at the maximal height immediately. You can see that this means that the surgery slope is the maximal one, that I won't go into, but it's fairly quick. Sorry for the cut. I noticed this after recording. I really wanted this omega n to be positive, either swap the numerator or make it positive. Also, in the argument to come here, I consider positive. I consider n greater or smaller than n prime, but I only really look to the right of, say, what does LRN do? On the right side. And something to keep in mind is that due to the hyperelliptic involution, this is really the same as what LR minus n is doing on the left side. So all cases are covered in case that was a concern. Sorry, I forgot to mention that. And then you can do the same thing for omega n, any other spin-C structure, and you could define this number of column count relative to some supposed figure 8. You're trying to pick the largest figure 8 that it could possibly hit, but even then, the expectation is that you wouldn't be able to match the grading difference. For brevity, I'll just go over the case when this spin-C structure that you select n is less than n prime. In this case, the column width is exactly the same, and in each column that you decompose the grading differences over, you get that the number of base points that they enclose is just n prime minus n, and then you're adding it up for so like the total length of the column that you have. And so it's easy to see when this omega n prime is large, this number can't keep up. It's sort of like the winding number is growing faster than the contribution from the weight of the grading arrow and from that term from before. So you either get that it's only one higher, and in that case, you had to have adjacent spin-C structures. In that case, the surgery slope has to be really small because you're spitting off a integer homology sphere summand, and those early examples sort of captured the behavior there. If it's greater than 1, then you get these unequal widths, and so you couldn't have any other spin-C structure besides n prime and minus n prime, the one that are sort of guaranteed to be isomorphic. And so that ends up doing it there. So once you have that only 2 spin-C structures can be isomorphic, the rest of the argument basically forces it so that this periodicity proposition requires that it associates n prime and minus n prime. So that tells you that the order of your h_2 of your y2 summand, that's got to be even. But the idea that only 2 spin-C structures have this feature anyway tells you that you have an RP3 summand. And those both can't happen at the same time, because otherwise you would be suggesting that you're having R surgery on some, not admitting something that it doesn't have cyclic H lower 1, which can't happen. So that's sort of the idea behind the techniques. They don't get too much more interesting when you incorporate non-zero tau, but hopefully I can speak about that in the near future. All right, thank you for your time.